All right. So we now have the ability to compare on a per molecule basis how much carbon dioxide was produced from burning our galactose or burning our ethanol, right? If you recall yesterday, that's what we learned is how we can balance those chemical equations, okay? But working with per molecules, while super important, and that's the way the reactions happen is on a per molecule basis. But when we go in the lab and actually try and do some work, we're not going to be able to measure the individual number of molecules. What do we measure when we go in the lab? Well, we don't measure moles directly, right? Because moles are a large number of molecules. We don't count molecules one by one. What do we measure? Grams. We measure the mass. Now, we can convert mass into moles. We know how to do that. So let's look at how do we combine these two things together. Two great tastes that taste great together. How do we combine working with mass and working with chemical equations? Okay? The nice thing about all this stuff is you already know how to do each piece. You've already done it. We are combining two little pieces into a larger problem. If we have a molecule of ethanol, we know that one molecule of ethanol takes 3 oxygens to react. And when that happens, when this reaction takes place of 1 ethanol with 3 oxygens, we're going to get 2 carbon dioxides and 2 water molecules. Okay? So, when we do that, if we light that ethanol on fire, okay, we're going to use up the oxygen. We're going to make carbon dioxide and water. But again, this is how we want to do it. We want to do it in large quantities because that's what we can do in the lab. So, we want to be able to take the gram values, the masses of these large physical quantities that we can carry around in test tubes and measure, and convert them into number of molecules. And you know how to do that. If I give you grams of ethanol, how are you going to convert it into?
Find the moles and then you multiply that.
Yeah, how do you find the moles? How do you find the moles?
Every chemical substance, a certain amount of grams, all the grams added together into balance.
Oh, but okay, the grams added together from where?
From the AMUs.
The AMUs from the periodic table. Okay? So you want the grams per moles from the periodic table. That's the conversion. That's what we use to convert to moles.
And then you multiply that by Avogadro.
And that would get us to individual numbers. Generally, stopping with moles is good. We can stop with moles because a mole is just a certain number of particles. It's like if we were measuring dozens of eggs. Yeah. So that, exactly. So what we want to do is now let's look at how we actually do that. And then we want to say, all right, if I have 100 grams of ethanol, okay, how much carbon dioxide is produced? What mass of carbon dioxide is produced? What mass of oxygen would I need to burn that up? So we know how to do this first part. If we have 100 grams of ethanol, we want to set up a ratio that converts the grams of ethanol, right, into moles. We want to convert the grams, so they were on the top. We need to make sure they're on the bottom. Where did I get this number one more time? From the periodic table. So I added the mass of 2 carbons plus the mass of 6 hydrogens plus the mass of 1 oxygen. Now, here's the thing. If I have moles of ethanol, okay, if I have moles of ethanol, and I want to convert, again, I want to do a conversion from moles of ethanol, okay, I want to convert into, say, moles of carbon dioxide. Again, I've got the moles here, so I know I want moles on the bottom, okay? But now I need a ratio. For every 1 mole of ethanol, how many carbon dioxides are there? So if I burn 1 mole of ethanol, I know that I will need, or I will produce, 2 moles of carbon dioxide. This we call the mole ratio. And it always comes from the balanced chemical equation. This ratio in the chemical equation, a 1 to 2, tells me that if I go in the lab and I measure out a certain amount of ethanol, I can calculate how much carbon dioxide will be produced. I can also calculate how much oxygen would be needed to react. The last step is to reverse this process. I remember grams canceled grams, moles of ethanol canceled moles of ethanol. I have moles of carbon dioxide. I want to take those moles of carbon dioxide and I want to convert the moles of carbon dioxide into grams of carbon dioxide. Where could I get a ratio that would tell me moles to grams? The periodic table gives me that information. I know that if I add the value of 1 carbon plus the value of 2 oxygens from the periodic table, that will tell me how much 1 mole of carbon dioxide weighs. I now have converted. I started with grams of ethanol, converted to moles. I used the mole ratio from the balanced chemical equation. And now I've converted back into grams. But now instead of grams of ethanol, I've converted to grams of carbon dioxide. If I burn 100 grams of ethanol, I will produce, grab your calculator and do the math, and we would get 191. You will need your calculator because I'm about to give you an example. Hey guys, shh. You need 191.1 grams, or will produce 191.1 grams of carbon dioxide. Now, this is super important to realize. Chemical reactions happen based on the number of particles. You cannot use this ratio with grams. Grams vary how many particles are in one gram changes. That's why we had to go through and convert into moles first. Then we can use the mole ratio to convert from one molecule to another. Then we converted back into grams because we wanted to know what mass would be produced. What if we asked ourselves the question, how much oxygen would I need? What would I start with? If I wanted to do this, and I'm asking myself the question, how much oxygen do I need? Where do I start? I start with the first part. And the first part is what? 100 grams of ethanol. And then what am I going to do with that 100 grams? I still have to convert it because I always got to convert into moles. Now, this is where it goes different. This is the change. Because I'm trying to, in this case, find the oxygen. So what do I have to do to find the oxygen? What is different about the problem now? Yeah. I need to change the 2 moles of carbon dioxide into 3 of oxygen. The 1 on the bottom stays the same because that's the coefficient on the ethanol. What if there was a coefficient of 4 on the ethanol? I'd have to put a 4 here. Okay? Question?
Why do you use ethanol? Why wouldn't you start with another?
So it depends on what information I give you in the problem, where you start. In this case, I gave you this 100 grams as that's how much ethanol we're going to burn. The problem has to give you something to start with. Right. It depends on what the problem gives you. And we'll see on Thursday that it's possible to start with both of them. Question? Somebody answer. Question. Ask.
You don't have to do like this when you're finding how much oxygen there is. Is there oxygen?
Well, the question was how much oxygen gas do I need? That was what I was really asking. Was how much oxygen gas do I need to add? But see, the nice thing is when I do it this way, it doesn't really matter how much is produced because I'm calculating based on this balanced chemical equation. This 3 takes into account both of these guys over here already. So I just needed to do this 1 mole of ethanol to 3 moles of oxygen. Now my last step, what's my last step? What's my last conversion I need to do? I need to go moles to grams. Moles of what? Moles of oxygen to grams of oxygen. And I would look that up, periodic table. Okay, so 1 mole of oxygen, 32 grams of oxygen. Grab your calculator.
There's a typo on this. It says 1 mole of CO2.
Change it. This is right. I put those in there intentionally to see if you're reading the notes. Yeah, but this is O2. There's 2 oxygens. 16 and 16 is 32. Okay? Sounds like we should see if we can do this ourselves. What mass of carbon dioxide would be produced from burning 100 grams of galactose? This is the equation. You already figured this out yesterday. This was the example from yesterday, was figuring out this equation, right? So I'm giving you 100 grams of galactose, milk sugar, and asking what mass of carbon dioxide would be produced. What's the first thing you want to write down? 100 grams of that chemical formula. Okay? So what did we start with in our example? We started with grams, we started with what I gave you. So I'm giving you 100 grams of galactose. And galactose is this stuff. So that's a starting point. Now replicate what we just did. How many grams of carbon dioxide? All right. So there are several different ways to set this problem up, okay? I am going to generally show you this dimensional analysis approach because I think it's helpful to make what we're doing very explicit, okay? If you want to calculate these in slightly different ways, like do each step and calculate it, that works and it's fine. You must show work, okay? On the AP test, you know, an overall problem, an big problem is typically graded on a 10-point scale, 8 to 10-point scale. An individual part, which might be a question like this, could be a part. This part might be worth 2 or 3 points. Let's say it's worth 3 points. You're going to get 1 point for having the correct number answer. And you're going to get 2 points for showing some work. If you show work and it's the correct work, you can earn those 2 points and you'll lose the 1. But if you get the correct answer and don't show any work, you got 1 point and didn't get the 2 for showing work. Okay? So, one way to show work is to do this. Right? If you write this out, that's showing the work. That's showing what you do. There are other ways. You could write each of these mathematical steps as an individual step. That's fine. It's exact same math as long as you're doing the right stuff. Okay? This has the advantage of allowing us to see and have a double check. And that double check is, are your units canceling out appropriately? Your grams of galactose should cancel grams of galactose. Moles of galactose should cancel moles of galactose. Moles of carbon dioxide should cancel moles of carbon dioxide. And the last thing, the only one we're left with is grams of carbon dioxide, which is what we're trying to answer. So, 100 grams, I use the molar mass, add it from the periodic table. Okay? I then do the important new bit. That's this mole ratio, which always comes from the balanced equation. So this is a trick, right? This one, molar mass comes from the periodic table. Mole ratio comes from the balanced chemical equation. Okay, that's where this 6 came from. And then I converted back to grams. How much oxygen would you need? How much oxygen would you need? I want to know exactly how much. How many grams of oxygen would you need to burn 100 grams of ethanol? So how are we doing? We got it? So what is different? What do we change? What part of this? Do I have to change? Do I have to change this part? Do I have to change this part? Do I have to change this part? It's the number stays the same, but that's just happenstance because this and this happen to be the same. But if this number was different, but we do change this isn't CO2 anymore. And the last part in particular, this is now O2, and it's 32 grams because it is O2. Okay, O2, that's the molecule we're talking about. I'm asking how many grams of O2, and it's 106.6.
Should we round all molar masses to 4 sig figs?
Generally, yeah, if you look at the periodic table from the AP test, it has 4 sig figs on it. And that's where I typically am going to go, because that's what you're going to use on the AP test and on our test as well. So if you look at the periodic table that I get handed out, 4 sig figs, that's what we're going to go with, because that's what you're going to have. At 4 sig figs. Depends on, like if something weighed in the hundreds, it'll only usually go to the tenths. But something like hydrogen, it'll go to the thousandths place. So 4 sig figs. All right. So it looks like, on a per gram basis, per gram, the galactose produces less carbon dioxide per gram. If you burn 100 grams of galactose, you only produced 106 grams of carbon dioxide. If you burned 100 grams of ethanol, it was more, right? So on a per gram basis. Now, what else might we want to consider when we're thinking about burning stuff for heat?
Which releases?
Yeah, how much heat is released? Because what we really care about is how much heat, how much energy do we get per gram of carbon dioxide produced. Okay? And so that's something we're going to need to wait a few chapters before we get there. That's chapter 6 that we'll look at right before winter break. We'll be able to answer that question. You don't care about global warming?
Like, I mean, at that age,
No, they're
care
very
about how much
knowledge fixed.
They're like my kids.
your kids are.
No, all right, so tomorrow, tomorrow we're going to spend some time practicing these problems. I have some worksheets to work on. But on Thursday, we're going to do our last bit here, which is we want to be able to answer this question. Okay? If I burn 100 grams of ethanol with 100 grams of oxygen, how much water could we make?
Wait, how do you get water from
It's not enough oxygen.
What are the products of our combustion reaction? Look at the sheet. Well, the water is released in the gas phase, but if we cooled it down, it would turn into liquid. Yeah.
Wouldn't there's not enough oxygen to burn all of it?
That's what we're going to have to worry about is, do we have enough, and how can we figure which one do we have enough of, and what does that mean? What we call limiting reactant problems. Okay? And that'll be our lecture on Thursday. And that'll wrap up chapter 3. We're going to wrap up chapter 3 on Thursday. And then on next week, we'll do chapter 4.
Oh, we're not taking a test.
They're a combined test, two-day, 2-unit test. Chapter 4 is all about different types of chemical reactions. So more balancing, different types of reactions, that kind of fun stuff. And we're going to learn how to predict what happens in chapter 4.
So I don't remember you guys saying quarter graded
Yeah, I'm going to definitely get the Scantron graded before next week on Tuesday, and then all the worksheets we'll get on there as well. Okay? Excellent.